So in this video, I want to share with you guys an experimental observation regarding the isodynamic points of a triangle. So everything is already drawn because this will take me some time to draw in this video, so I'm just quickly going to go over the properties here. I'm going to start with a triangle ABC right here in the middle, whose vertices I can move around by just dragging them, like so, okay? And what I'm going to do is I'm going to erect 3 regular hexagons on each one of the sides of ABC. So here's a first regular hexagon erected on the side, meaning that one of the sides of this regular hexagon is precisely the side AB. So this is a regular hexagon, all the other sides have the same length, and so forth and so on. And I'm going to repeat this construction, erecting a second hexagon on side BC and a third one on side CA. Now, a first observation here is I can certainly locate the centroids of these 3 hexagons and draw this red triangle on the centroids. A very pleasing observation is that the red triangle is perspective with the reference triangle at the first Fermat point, or X16 of ABC. So what I did here is I actually drew straight lines from corresponding vertices of my centroidal or hexagonal centroidal triangle, the red triangle, through the corresponding vertices of my reference triangle, and I noticed that these 3 lines, they converge, they concur, okay? And I noticed that after I did some analysis that this point was actually X13. So this is a first observation. A second observation is that the circumcircle of this red triangle has a center on some obscure point X627, and I found this numerically. It's not germane to this video to actually dwell on this particular fact, but there is a name for the center of this red circle, the red circumcircle of the triangle of centroids of my erected hexagons. Okay, so this is fact number 2. Fact number 3 is I'm going to now define these 3 green triangles which sit between 2 consecutive hexagons, right? You can take this hexagon here, take this very first vertex over here of this first hexagon, and connect it with the 5th vertex of the next hexagon. So let's say I'm going to actually traverse my vertices in counterclockwise fashion. So I'm going to call this my first vertex of this hexagon, and this one over here, the 5th vertex of the neighboring hexagon. So I can connect these 2 consecutive hexagons, and I'm going to call this interstitial space the first flank triangle, okay? Or this is the B flank triangle of my construction. So it's this green, shaded green area here. So here's my C flank triangle, constructed the same way. It's the interstice between these 2 hexagons. And here's my A flank, interstice between, or the interstitial zone between these 2 neighboring hexagons. Okay, so I have these 3 flank triangles, and this term flank has been used in previous constructions that erect regular quadrilaterals or triangles on the sides of a triangle. So here I'm actually erecting hexagons. Okay, now I have these 3 flank triangles, and the second observation is, let me now compute their first isodynamic points. So here's X15 of this B triangle, here's X15 of the C triangle, and here's X15 of the A flank triangle. Okay, and I'm going to connect those 3 guys and make them be the vertices of a second triangle we're going to study. Now, the second observation is that the triangle formed by the X15s of my flanks is perspective with my reference triangle ABC at the symmedian point X6 of my original triangle ABC. So that's pretty nice, right? I can actually move ABC around. I can, just watch what's happening here, and I can see that indeed when I connect this vertex of my X15 flank to A, and I extend this line, and I extend this line, and I extend this line, I do see that this green flank X15 triangle with my reference, these 3 lines concur, and they concur on X6, on the symmedian point X6 of my reference. So that's pretty nice. Now, what I did here as well was I drew the circumcircle of this green triangle. You can see here that it's drawn dotted green. And I try to identify numerically here if it was one of the first 3,000 points in Kimberlin's list, which you can do this with a command here in GeoGebra. But I could not identify that number, so I'm going to leave this as a question. What is this point, which is the circumcenter of the triangle formed by the 3x15ths of my flank, hexagonal flanks? So I have it here as x question mark. I don't know what it is. All right, so the third and very last and perhaps most surprising observation here is the following. If you actually were to draw the second isodynamic points, X16s of the 3 flank triangles, something magical happens. They all coincide at this point. So if I move my triangle around, I have a common second isodynamic point of the 3 flank triangles. So this entire construction is conspiring to create this algebra geometric harmony, right? Why is it? What is so interesting about these flank triangles that for any choice of A, B, C, the 3 isodynamic points coincide? And I don't know, and I'll invite the viewers to perhaps work out a proof. Of course, this X16 does not need to be external to the hexagons, it can be internal as well. But the fact remains that the X16 of the 3 greens, they all coincide at this particular point. How do we actually construct this point? How do we prove that they're actually coincidental? Okay, so this was an example of a quote-unquote researchy kind of observation that is Euclidean, right? It's an Euclidean, sort of an elementary Euclidean construction that uses the first and second isodynamic points, and through them we can actually learn or discover a lot of really neat things about the triangle. So I'll see you in the next video.